Hello and welcome to the latest Bic Gardner web seminar. My name is John Kowalski. I'm part of the marketing team here at Bic Gardner and like to welcome you. Today we're talking about medium milling, taking a deep dive into it. This is really the second part of our dispersion series. The first part that we ran, it was probably 3-4 weeks ago. If you missed that, if you're interested in that, we do have a YouTube channel. We'll send you a email with that link so you can check out previous recordings. But for today, our format, it's a longer presentation than our office hours, 40-45 minutes, then followed by questions and answers. If you do have any questions, please log them in the chat box. And, hi, Andy. And then also, we are recording this immediately following the presentation. You'll receive an automated link with that recording. Feel free to share it with colleagues, watch again later. It's great for date night, I hear too. So, you know, whatever works for you. Our presenter today is our dispersion expert within the organization, Mr. Andy Stummer. He is our business line manager for dispersion. So, Andy, there it is, sir. It's all yours. Take it away.
Hey, John, thank you for the introduction. Welcome, everybody. Like John said, this is the second part of our milling seminar or dispersion seminar, and we'll cover this in a little bit more in depth. And at the end of the presentation, please feel free to ask questions, and hopefully we'll get through all of them. But we're going to start with a quick introduction about the company. So we're going to then dive right into the dispersion process. Just a quick overview, not too much in depth, just a little refresh about the first part of the dispersion process before we talk about actually the milling part. And then we're going to cover the lab and production equipment capabilities that we offer, quality control, as well as standard lab capabilities in our Wallingford or German facility. So let's go through it. As you can see in the slide right here, we cover everything from small lab space all the way up to pilot and to manufacturing. There was actually much larger manufacturing units, but they just didn't fit on that particular slide. So the company VMA is a German company. They were founded by Hermann Getzmann, his beautiful wife up on the top right, in 1972. He actually was a co-founder of Anton Paar. He decided that he would want to start his own company and sold out and basically started the VMA Getzmann company in Reichshof, Germany, which is about 30 miles east of Cologne. The very first Dispermat down below here was designed or manufactured in 1973. Believe it or not, there are still some customers that are still using the original Dispermats. The motors are direct drive, they're brushless, there is no belts, so they are really low maintenance and will last a lifetime. And also very, very quiet because of the design. The only component that some of these customers had to replace that are still running on the original units were actually the control box that you can see right here. That's the original one, so they updated those. We had a number of customers recently that did that, but they're still running, believe it or not, on the original Dispermats. BIC has had the exclusive distribution rights for US and Canada since 1988. The way this started was we brought some over to our big additives facilities to use in our applications laboratory, and we had customers come in and review the process, and they were asking about the Dispermats, and that's when Dr. Peter came up with the idea to actually bring them over to the US and offer them through our big instruments division, or Bic Gardner, as some of you are probably familiar with. And that's how we got that product line introduced here in North America. The company is still owned by the same family. The two kids, Christian and Martin, are now running it. They have about 100 employees, actually a little bit over 100 now. They added some more designers. And on the next slide, you'll see that some of the added capabilities, but they are known to make high-end dissolvers, bead mills, basket mills for the lab space pilot and as well as manufacturing environment. So that building here in the middle, that back part is actually new. So they added 2 floors and added more design capability and more manufacturing space. One of the things that makes VMA Getzman stand out is that about 40% of everything that they build is custom. So we have a lot of different customers from different end use markets with different requirements, and we're able to satisfy a lot of these different needs by making custom designs of the equipment. And then we have the state of the art dispersion lab here in Wallingford, where I'm at today, as well as in Reichshof, Germany, at the headquarters. So that lab is right up here, second floor. Um, so just a quick overview. So why are we dispersing? Obviously, it came out of the coatings world, has since branched out to many different what we call end use markets. But basically, it came out of the coatings world and to really disperse different types of pigments. So we differentiate there between the organic pigments, inorganics, functional, and then some of the newer special effect pigments, as you know, then a lot of your cosmetics or automotive applications like the silver paints. Um, a lot more care has to be taken because we don't want to destroy these special effect pigments if we put too much here, or with the media, sometimes they get destroyed, and that's what we want to avoid, to really just maintain the pigment integrity. The goal is really to improve our gloss transparency, have better color stability, textural strength, or cleanliness of shades are some of the attributes that we're looking for when we're properly dispersing our mill base. So the goals are really to improve our wetting. That's the first step. We want to break up these invisible electromagnetic forces. They're called Van der Waals forces. They are binding forces that hold our pigment particles together. And the goal is really to reduce them ideally back to the primary particle size, which will give us improved color, a better gloss. We'll have, as a result, overall improved appearance. We're going to save money because we're going to be more efficient in our process. We'll need less pigment the finer we disperse. So that's a cost saving mechanism. Again, reduced raw material costs. We're going to have better product consistency. It's going to help us improve our formulation. A more consistent particle size distribution is also a net result of proper dispersing. And then obviously we want to get really good upscale results from the lab to pilot and then all the way up to manufacturing. So some of the issues that come up if we do a poor job dispersing our pigments or particles, we're going to have very poor stability. We're going to have maybe shift in our color. That comes up a lot, flocculation of pigments where they just bind back together and then they settle out, so they don't have any shelf life. Sagging, leveling, settling is another issue there. Reduced gloss levels or the separation could be another issue if we poorly disperse. But I want to also stress uh, proper dispersion process is only one part of the equation. We also need to add the right additives to make sure that we have a properly formulated product and it stays that way, not that it changes after storing. So it's really important to remember that we want to have good stability. So pigments that require strong color fastness to reduce fading over time. So that's really important. Brightness, this will provide the best color usually. The rule of thumb for pigment size is that the smaller the particles, that will improve our transparency, we'll get better color, and obviously we'll need less of the pigment in our formulation, helping us to save money, which our accountants really like to hear, or the purchasing department. And then viscosity also plays a big role. So the lower the viscosity, usually is better during our dispersing or milling process. But we don't want to go too low because uh, we want to be able to put enough energy. And if our mill base has the viscosity, let's say, of water, we need to add either more beads, or we put in more time or more energy uh, to really process the material. So there is a sweet spot, and we're looking anywhere between three, maybe to 10,000 centipoise is really what we call optimization of the mill base. And that's usually where we want to be in order to properly disperse or mill our material. If we get too high with our viscosity, we run into the problem that we won't be able to properly move the material in the container. If we horizontally mill, we won't be able to properly push or put the material through our horizontal milling chamber. If we want to use a basket mill and the viscosity is too high, then we're going to have a problem with the flow of the material in and out of the basket. So we always want to make sure that we maintain a good range of our viscosity to make sure the product is flowable. So it's therefore very important to remember that we're only trying to reduce our particle size and not destroy our particles. That is not the goal of dispersing and milling. Our agglomerates and the smaller clusters, we call them aggregates, they are really reduced to primary particle size, and only the shear forces are responsible for that separation, nothing else. And then at the end, we want to select the right additives to keep the primary particles in a suspended state and have a good looking product. So here's just an example of different pigment types and what that looks like in terms of particle size, just to give you an idea of what that looks like under the microscope. And I really like this slide a lot because it kind of shows what's happening here. So we have these larger building blocks. These are these clusters that are held together by these van der Waals forces. We call them agglomerates. And ideally, what we want to do is we want to reduce those, break up these binding forces and reduce the size of these blocks and turn them into aggregates. In order to go from the agglomerate level to the aggregate level, we need to use a cow's blade or an impeller disc. That will help us get there. To go from the aggregate level down to the primary particle size, the impeller or the cow's blade no longer gives us sufficient shear. So therefore, we need to do what's called medium milling. That's what we'll talk about today. And that's that step from the aggregate down to the primary particle level, where we need to use media and a milling disc and different types of milling systems that are available to get that job done. So the first step is we need to wet our solid particles. That's why that dispersion, pre-dispersion process is so important. It allows us to mechanically break down these agglomerates and then turn them into aggregates. And then furthermore, for milling, we go then down to the primary particle size. And at the end, we want to stabilize our particles again with the right additive for your formulation. So here is also a good slide just showing you the entire dispersion process. So we start out with the blade. That's where we wet our particles and break up these larger agglomerates. And then when we want to go to the fine particle size, we need to do the milling. In this case, you see a horizontal rotor. There's other milling options, and then basically that allows us to break down the particles really fine. Even nano range is not a problem. And then we want to stabilize it. So this slide is kind of a good slide in showing you or outlining at what point you're gonna or you should move over to a media mill. So you start out, let's say, with a very coarse material, and then you can use a dissolver around 20 to 30 to 10 microns in that range. At that point, you should start media milling. That's when you're more efficient. And as you can see, the dissolver stops at around 10 microns. And then we're not really putting in enough shear anymore to really help us go down to the sub micron range or small micron range where we want to end up. We need to really medium mill. So for the pre-dispersion process, it's important to remember it's not only the RPMs, that's only one part of the equation. what we're really looking for is the actual tip speed, because the RPMs are just only one variable. But what really matters is what is the diameter of your blade and what is the actual tip speed. So we want to be between 18 to 25 meters per second to use a dissolver. So we have different types of dispomats. And then for fine dispersing and milling, we want to use our either basket mill, a vertical bead mill, or a horizontal mill. And then the tip speed should be anywhere between 10 to 16 meters per second. That's when we are medium milling. That's really important. These are numbers that are derived from many, many years of uh, trialing different formulations, identifying what gives us the best milling results over time. So these are really, really good numbers. So just briefly, before we mill, we want to also make sure that for our pre-dispersion process, our dissolver blade is in the right ratio with our container. So we have on the right, here's a good example of the different container sizes down here, and then what type of blade you could use depending on the container side and also depending on the viscosity that you're running. So there is not one blade that fits all. So you have actually quite a bit of flexibility in terms of what blade diameter you want to choose for your vessel size. And here is the important calculation formula to calculate our tape speed. So we have pi multiplied by the diameter of our milling disc by the RPM or the shaft speed. If we want to get meters per second, how it's displayed on our machines, we want to divide everything by 60, but keep in mind that to express the diameter of our blade, we want to use metric and in meters. So if let's say we have a 50 millimeter blade, we want to use 0.05 in that case, multiply that with pi and the RPMs, and then divide that by 60. That will give us our actual tape speed in meters per second, which should be anywhere between 18 to 25 meters per second for pre-dispersion, or 10 to 16 meters when we actually medium milling. That's a really good formula. On our higher end models like the AE or the CA, that is already calculated and shown on the display. On the more lower end or medium models, that number has to be calculated. So here is the donut effect, very important. So we'll talk about that in a second, but we want to optimize our dispersion before we go actually into the milling process. So duration of the dispersion is important, usually anywhere between 5 to 15 minutes, depending on your mill base. That gives us really good wetting. We want to see a donut effect. That's the visual cue that we see when we look inside of a container, that it actually looks like a donut. Then we know we are actually optimizing our pre-dispersion process of 18 to 25 meters per second. So if the viscosity is in the range I talked earlier, about 3 to 10,000 centipoise, and we stay within the tape speed range, we'll have a really good looking donut, and we would know that we are properly dispersing our material. Then again, the geometric consideration. So we want to use the right diameter blade, container ratio. We also want to use the right type of impeller disc. There's different types out there for different viscosities. Mill base should be about 50% fill ratio of our container. We don't want to go much more. We can go up to 70 maximum. But if we go higher, we have an issue with potentially spilling, especially if we add a lot of shear force. From a formulation standpoint, pigment and filler concentration play a big part. We want to keep the temperature as low as possible, especially when we're dealing with solvent-based materials. We don't want to flash off all the solvent. We want to keep it in our mill base, so we try to keep the temperature lower. And then again, we want to choose the right additives for better wetting, dispersing, and no flocculation of our pigments. And then when we have the right particle size, that's when we actually should start the medium milling process. So the difference here between the dissolver and the bead mill, as you probably already know, our our dissolvers, they're called dispermats. You can use them for both dispersing as well as milling. That what makes them really unique. And So when you use them as a dissolver, that's the first step in the dispersion process, pre-dispersion. We can only apply limited amount of energy because of the blade. Um, that means limited shear force. It's really only there to de-agglomerate, not to break up the aggregates, to get down to the primary particle size. And it is a necessary step for any proper dispersion to do before you're starting to mill. Um, Not saying I learn something new every day. In some cases, you can do it, but it's not advisable because you get much better wetting when you use a dispersion blade. Um, so the process to do it correctly would be to first pre-disperse, make sure you get to the right particle size range, and then you want to start milling. You will find that milling will also be more efficient if you have the right particle size to start with. And then if you only use a dissolver and no medium mill, your color strength would be limited. For example, poor gloss, haze, some of these issues we talked earlier could be a factor if we are not milling. Now, in our medium mills, we can put in a lot more energy. We really break down the particles to sub microns if we want to, a low micron range, primary particle size, and that will give us a much better looking product. Not only better color strength and transparency, particle size distribution, but I want to also add probably better mechanical properties as well if we do a better dispersion job, milling job. So what actually happens in a bead mill? So as you know, we use media that is either zirconia based. Some people use glass, which we don't recommend for various reasons. We'll cover that in a minute here. But these beads are perfectly round under the microscope, or at least they should be. If they are not, then maybe you need to look for a different supplier because it's really important that you have high quality zirconium beads, either cerium stabilized or yttrium treated. There's the ones are white and then the other ones are brownish in color. Um, but that is really important that they are perfectly spherical. So as you're milling, inside of your milling chamber, it's a basket mill or if it's a horizontal bead mill, these beads drift around your slurry at very high velocities. And they get pushed towards each other and then they drift away from each other at really high velocities. So that drifting action is actually what's producing the shear. So think about it this way: if you know the rubber duck syndrome in the bathtub, as you try to squeeze that rubber duck and it always tries to escape your hands, it's very hard to actually catch. That's exactly what's happening inside of a bead mill, except at much higher speeds, a lot more force, and that action with as the beads drift towards each other is causing these particles to just shear away and break up these binding forces. That's really what's happening inside of a bead mill. We're not trying to crush our pigment particles. We're only trying to break up these binding forces. That's really all that we are trying to do, and that's what's really happening inside of a bead mill. Actually, the probability of a pigment particle to be wedged in between two beads at the same time when they're colliding is very, very slim because of the fluid dynamics that they are getting pushed away. So, really, that pushing action is the force that's causing the breakup of these binding forces. That's what's really happening there. So kinetic energy is very important. Um, Maybe you don't have to write it down, but we'll talk about that in why that is important. And then you can download the presentation later, so you'll have that formula if you want to figure out the kinetic energy. Uh, but the reason it's important is because different beads have different weights. And the reason we want to use ceramic beads and not glass beads is because they have a higher specific gravity. They are heavier, the same size. Uh, so imagine if you're trying to drive that nail into the board, using a very small hammer, it sometimes may be impossible to drive the nail in the board because you don't have enough kinetic energy to really get the nail down into the board. If I use a sledgehammer, it takes me one blow and that nail will be in the board, right? So it really is about selecting the correct uh, diameter or bead size to really properly, um, disperse or mill our material. But that's kind of like the same thing. So in the milling process, so therefore we always want to get beads that are heavier. That means we have more kinetic energy, and that will give us more milling action and more efficient milling action. So if you compare glass, you have a specific weight of 2.5. The serum stabilized zirconia is 6.1, almost 3 times as heavy, right? Um, so that alone will tell me that I have a lot more milling action with my zirconia bead than with my glass beads. The other problem is the hardness, right? So my Vico hardness is 1150 on my zirconium. On my glass, it's only 400. What does that do? During the milling process, obviously, there's a lot of shear. The beads get thrown against the milling chamber. Some beads collide. They impact with the rotor. So over time, either they wear down or they will also break. We haven't seen really zirconium beads break, but we have seen glass beads break all the time. And then what happens is you end up with shards of your glass inside of your mill base. Not very good. It contaminates your slurry. Uh, you have uneven processing parameters because you can no longer guarantee that all the media is the same size. So if you try to replicate a process, it's difficult to do with glass. You have to recycle them a lot more often than zirconium. The only upside to using glass is they're quite a bit cheaper, but not nearly as effective as zirconium. Therefore, we don't sell glass and we advise against glass beads for these differences compared to, or problems compared to zirconium. So I like this slide a lot because it shows you the actually what's happening when these beads in the milling chambers. You have large beads, right? And the small particle right there on the in kind of the center is actually an agglomerate or an aggregate, and we're trying to break that up. So by that shearing action, that it's actually happening right in these corners right there. So if we have beads that are too big and our particles are too small, it's very difficult for them to shear properly. That's why you have to adjust and dial in the right media size compared to your starting particle size. Uh, it's not impossible, but it's not great to use if the beads are too small and your particles are too big. Again, the kinetic energy comes into play. You're not going to be able to really break up these binding forces because your particles are too large, the beads are too small, not enough energy. But the opposite could also happen if your beads are too big, then the area where they're supposed to be sheared is too big. So therefore, that energy gets lost, and therefore you have diminished milling results as a result of that. That's the downside of having beads that are too big. So these are some of the key uh, elements that are really important to remember when we're milling. So particle size after the pre-dispersion process with the dissolver, again, 10 microns is really your threshold there. We can't really go any lower or we're not properly breaking up the particle size. Bead size and weight, again, kinetic energy. We want to use the right size beads. Um, the bead type, stay away from glass. The volume of the beads, depending on if you're using a vertical bead mill, you can add a lot more beads, up to 100% of mill base. If you have a basket mill, you have maybe half of that volume. Uh, then you also have a horizontal bead mill, depending on the milling chamber volume, but you also have a certain amount of beads that are required to have proper milling. And different horizontal mills have different bead requirements, so that would be something you can find in your manual. The shape of beads, very important. We always want them to be perfectly round, not no edges, so they should be really spherical. Again, stay away from cheap, inexpensive beads. We have seen cases where people buy them or will get a sample, and then the supplier, when they order the first lot, the sample look totally different than the actual lot that they order, and they are no longer very um, balanced and round. They now have edges, and they're not ideal for milling. Again, when we are milling, our tape speed should be about 10 to 16 meters per second. Again, the calculation for tape speed is the RPM multiplied with pi times the diameter of your milling rotor in metric. So let's say it's a 50 millimeter rotor times 0.05 and divide everything by 60. That will give you the correct tip speed. Uh, Product temperature really important. Try to stay as cool as possible, especially when we are milling. We're putting in a lot of energy, and therefore we really need to maintain a proper temperature in our milling chamber or a supply vessel. They'll have all cooling jackets to really ensure proper temperature control of our mill base. Energy input is very important. How much energy I'm putting in. So either it's increase in speed or just increase in energy. We can, on some of our models, we can select the amount of energy we are putting in instead of speed. So as your viscosity changes during the milling process, the machine would automatically adjust the speed to always maintain the same energy that you're selecting. Let's say you want to mill with 1000 watts of energy, then it automatically adjusts the speed to always maintain the 1000 watts of energy, irrespective of your viscosity change. Number of passes, how often does it go a cycle through my basket mill or my horizontal medium mill? Milling time, very important. How long am I milling? We have cases where we need to mill for hours on end, and then we have cases where 5 minutes of milling time is already enough to give us the proper particle size. Depends really on your mill base and formulation that impacts that parameter. Uh, Again, the viscosity is very critical. If we are too low in our viscosity, then we have a problem putting in enough energy. If our viscosity is too high, then we're having a problem with flow of the material through our milling chamber or our basket mill. Uh, so again, milling diameter of our milling tool is also important. Um, we want to select the proper diameter that gives us the best ratio to our milling chamber. Um, the type of material we select. So we have anything from stainless steel, hard steel, ceramic, to also polyurethane or other materials. I want to stress that milling is very abrasive, especially if you are milling white materials. You can have an issue with discoloration where you will see all of a sudden gray appear in your slurry. We just recently saw that again with the customer, and it's really a matter of using them on white colors, zirconium light milling chamber, white ceramic to avoid any type of discoloration of our mill base. Unfortunately, this is unavoidable if you're using stainless steel, as the media would, hit the container walls or the milling chamber, and that will wear down that metal tiny particles into carry over into your slurry. So if you want to have good color stability, I highly recommend, or we highly recommend, that you use uh, ceramic components. And then again, different media mill designs depending on what the application calls for. So we have vertical mills, horizontal. Also, we have a basket mill design. Depending, different applications require different types of bead mills. So just a quick slide to show you the benefit. The Dispromat right here is the Dispromat AE. It can function also as a rotor stator. You can add a vacuum system. We can add a basket mill system, a wall scraping system for really viscous and thick materials. And we can also integrate a vertical bead mill called the APS, stands for air pressure system, that is also a milling system that will fit right onto our Dispromat. So one machine fits all the different needs for different applications. So it can be used as an homogenizer, like as a mixer, to blend two different liquids together with different attachments, either a butterfly or a propeller tool. We can also use it with the rotor stator as an emulsifier to blend one liquid into another liquid that's non-soluble at a very high shear rate. That's called emulsifying, or as a disperser, where we are actually breaking down the particles, what we're talking about today, and use it as a dissolver, or with a milling disc or a basket mill as a media mill. So very functional. So what's happening inside of our basket mill? So on top, first of all, you see it's a batch process. It's not continuous like you would have on a horizontal media mill. So there is a limitation as to how much volume you can process per trial. Um, you have your basket mill. Um, on the top, there's an inlet. Right below the inlet is a pumping wheel, and below the pumping wheel we have a milling disc. And then underneath the milling disc, we also have a screen. And below the screen, we have a cow's blade. So the cow's blade is not there to disperse the material, it's there to really suck the mill base out of the mill through the screen and then pump it back around to the top, where then that pumping wheel takes over and sucks it back into the basket. So you have very good movement of your mill base in and out of the basket. So that gives you many, many cycles through the basket mill and is very, very efficient. Um, Provided that I have also good viscosity. Now imagine if my viscosity is too high, then my material would cake up right here and I have no way of moving the product into my basket mill. Or it's not moving at all. If it's very thixotropic, we have seen the material kind of stagnant around these bars right here and not moving properly, then it's also very difficult to use that type of a media mill. However, if we have good flow, a basket mill is a really good alternative to a horizontal media mill or a vertical bead mill because it's very easy to operate, also very easy to clean, and we get very efficient milling results. As a matter of fact, we can go down to about 500 nanometers with the standard TML. We call it our basket mill system. If we want to go lower, then we really need to use either horizontal media mill or a vertical bead mill. Um, you can see cooling is very important because of all the energy we are putting in. So we have here a double walled milling chamber, and these bars right here, they're actually cooling lines as well. So we have water or coolant in, going through the basket all around, and then coming back up the other way. So therefore, we always maintain really good temperature inside of our milling basket. We also offer a nano kit with a different mesh size for very small media, and that basically allows us to really mill down the material super, super small into the mid to low nano range. Also very easy to clean. So here is a great slide showing you the milling action. We draw our mill base into the container. You can see our media is already in here. You didn't see that on the previous slide. If I forgot to mention that, I apologize. But you also fill you have to fill in the milling chamber here with media. So that comes in from the top. And then here you can see the media on this slide right here. Okay, again, sucking it out of the basket. The screen here keeps the media in place, and then we'll bring it to the top where then we rotate it in and out of the basket. That's the benefit of a basket mill. Very good, efficient milling. This is a larger production size basket mill. Our bead loading is right here where that screw sits. We remove the screw, we take a funnel, and then we feed the beads right into that gap right there. And that's the production size basket mill. So it's a batch system. It's a very simple design. We don't have any bearings, uh, no lip seals, no O-rings that can wear out. So it's very easy to maintain compared to a horizontal medium mill where we have all these different, components that we have to swap out. Here, you don't really have to do much except sometimes replace the milling disc and the pumping wheel, and occasion maybe the screen wears out. But that's the only thing you need to replace, but not often, depending obviously on how much you mill. But for example, my lab here, I mill quite a bit, and I have yet to replace the milling disc or the pumping wheel or the screen on my medium mill that's 4 years old. Um, with the DL shaft, that's the attachment that uh, goes onto our dispermat that would allow you to mill and disperse with one machine. So you go back and forth like that bayonet style quick change system. Uh, Very easy to handle. Uh, the baskets, again, are all double walled for proper cooling, except the smallest one, the TML05. Unfortunately, we don't have cooling capabilities. You just have to cool through the container, which needs to be double walled as well. And then we can have that nano kit for very small media if you want to mill down that small nano range. Then we can go into manufacturing. We can go all the way up to 2,000 liters of material. Very quick product change. We have what's called a quick change system, QCS for manufacturing, where we can go very quick from one basket to another basket. So if you're running multiple color families, it's very quick and easy to replace that. We have a vacuum system also if you want to mill under vacuum. That's sometimes helpful. Uh, if you want to remove the air, you get a little bit more milling efficiency. Imagine the air bubbles are tiny little air mattresses, and the beads that impact, those, they act like little buffers to reduce the milling efficiency. Here is a great system called the TML. That's for manufacturing. That's a two-in-one system. So you have your cowl split is right back here, so you can disperse and mill all on one machine. Very, very efficient. You don't have to replace the basket. This is great if you're only producing one color and you want to do a reasonable volume and you don't want to change colors. This is excellent because you pre-disperse. When you're ready to mill, you push the button on the control board, and then the basket comes down, and now you have a fully functioning media mill. You don't have to make any changes whatsoever. Very, very efficient. Uh, Vertical bead mill APS, that's really for smaller volumes. That's a lab scale model right here that again would fit up onto our disper mat. Here is our milling disc. We have a cover. We have a container that is separated with the screen on the bottom and the drain plug. And then we have a container below. It sits on a stand, but for sake of understanding this picture, they had to remove one of the legs so you can actually see what it properly looks like. But rest assured, if you purchase one, it has four legs. Um, so the top container has a screen on the bottom with the drain plug. So you will do your pre-dispersion in here. You just have to use a cowl's blade instead of a milling disc. And when you're ready to do milling, you just pop on the milling disc, you add your beads, put down the lid, and then you're milling. When you're ready to uh, remove your material, you hook up an air hose right here to the cover and pressurize your container, and then remove the drain plug, and then you're basically purging your mill base or slurry out of the container into the container below. That's a really nice way of milling. It only keeps the beads back in here. Then you add water or cleaning fluid, whatever you're using, put the cover back on, and then you basically run it for a few minutes, rinse and repeat. That's how you're actually cleaning the APS system. So it's very easy to clean, very easy to maintain. Again, like the basket mill, no real lip seal, no O-rings, any type of wearables like that you would have with the horizontal bead mill. Here, you don't have really any variables, only your screen on the bottom. We offer those APS systems also in ceramic configuration, so ceramic line milling chamber. Again, if you're just using stainless steel and you're running a white color, then you can have gray ending up in your slurry coming from the actual container wall that will then impact the color of your material. So here is kind of a, a graph that shows you what that looks like with the drain plug. It's very easy to remove. Here is your slurry with your media, your milling disc, and when you're ready to purge the material, just hook up that air hose to the socket, remove the drain plug, and then very nicely you can remove your mill base into the container below. So using air pressure for that, uh, we can go up to 7 liter container. We have made custom versions up to 30 liters, which is about 8 gallons. And we also have, obviously, like I explained, different configurations for ceramic if you want to get that line. And you can add 50% of material and 50% of beads, so you have 100% bead loading with respect to your mill base, and that's a very, very high bead loading, very good milling efficiency, able to go down to nano range, very narrow particle size distribution. The only issue is if you want to make more than, let's say, 30 liters, it gets difficult because of handling, because you need so many beads. So therefore, this is not really something we recommend for large scale production, maybe pilot at the most, but really more designed for lab scale to really prove out a concept and see what kind of pigment, concentration and so on works best in that formulation. And I want to do a quick milling and easy cleaning. So that's really, really designed for that. It does a great job. But we have customers that use it for small volume production, like pilot, like up to 30 liters. We have made custom systems. Okay, here's another slide. So different milling discs are available. Uh, Again, they fit right onto our disper mats from DMA. We can do very, very small volume with the lowest APS down to 12 milliliters. Very fast, easy cleaning. You can use a range of viscosities, even very thick viscosities work really well with the APS. We can get a nano screen. Um, we can get ceramic again. It's great for R&D and QC, not so much for production because of the handling. Again, easy cleaning and easy handling for quick color changes, but not production. And here are just example of our horizontal bead mills. So that's the SL. We have that in our laboratory in Wallingford. That's more of a large scale production horizontal mill. So the way it works, we have our supply vessel right here. On top of it is our agitator and pumping wheel. So that basically pumps the slurry that's in here down into our milling chamber. That's where we have our rotor. And then we basically circulate the product back into our milling chambers. We have a really good circulation in and out of the supply vessel into the milling chamber and back around. You can also set it up for pass-through mode, so you can just go through it once and then put it to another mill with maybe smaller beads, or you are done already after one pass. Unlikely, but there are some products that might behave that way. So either pass or recirculation method on a horizontal medium mill. The pumping system is integrated, so that's really nice. Uh, we can go up to 6,000 RPM. The independent control of our rotor and pumping speed. We have offer also different linings, ceramic, hard metal, stainless steel is standard. Sometimes we have customers that want polyurethane. They want a softer material. We can use a different range of media sizes. We use also a dynamic gap on ours. We don't use a screen to separate the media from the slurry. We actually have a dynamic gap. It's basically a machined, uh, looks like a little flange that goes in there, and that basically keeps the beads that are larger than that gap back in the milling chamber. So that helps with screen wear and is generally an improvement in design of our horizontal media mill. And then you can also get a nano kit if you want to go to sub 100 nanometers. You can't do it with the standard. You really need the small media and the nano components for that. Quality control briefly. So we have different control capabilities. Here on the right is just standard RPM, amperage, temperature. That's more manufacturing. Or we have here what's called our C technology, where we have a lot more features on our screen. On top left, you see the RPM. We have the energy in watts. Below that, we have actually our torque value in Newton meters. We get our tip speed displayed. That's really important. Temperature and timer function. So we can also program recipes. We call them at a later time. So a lot of different capabilities with that technology. And then we have the ability to also, on the higher end models for production, to program our own process if you want to integrate a scale. So there's different programmable capabilities that we offer. Also, lead time, I think, is a year on that Siemens controller, so not very advisable. We can program cutoff values with our higher end model, meaning that, let's say, if we want to, we don't want our material to exceed a certain temperature, we can program a value, a number of values, and say a warning. Let's say we want to have a cutoff at 80 C. We can warn at 50, that was 60, at 70, and then at 80 it shuts off the machine, or we can program it to run at a different speed. We can do net power calibration as the machines run without any product. They're already consuming energy and they are actually using power to operate. So if you're looking at the energy and you want to do a zero calibration, you can do that. And that means you run it for about 20 seconds. And then it basically takes all the values it needs to operate itself without product out of the equation. And then you'll know that all the values that are displayed are strictly related to your product. We can also send the data over to a computer. This is the 2007 version. We don't have the new one ready yet. It's called WinDisp. That's why this looks dated, but there is a more up-to-date version as well that's coming out called WinDisp. I think WinDisp 11. We have a lab space in Germany. That's our DMA headquarters. A lot of good capability to try different things with different types of equipment. And we have one in Wallingford, Connecticut, where we added new capabilities. So you can see back here all the different attachments. We also have a horizontal medium mill back here. So here's some of the new equipment that we have in our Wallingford lab. The latest AE, which is our flagship product for dispersing and milling with the basket mill or vertical bead mill. And we also have our horizontal medium mill. And so you can come to Wallingford to see the lab, try out experiments, run your material on our equipment. We can also include our chemists from our different end use markets to give you maybe some formulation support if you need that or are looking for that. We have those resources available. That sets Big apart from some of the competition. We're not just a hardware company, we're really a company that comes in and wants to offer a turnkey solution to help you get a better product, and have the best confidence in the process. And that's it for today. I think we went a little bit over in time, but hope answered a lot of questions.
Yeah, that's all right. All good stuff, Andy. Appreciate it. Thank you. A couple questions here. This was towards the beginning of the presentation. Brittany comments, viscosity at what shear rate?
That really depends on the product, so not sure
Okay.
to give you a correct answer. Usually we're talking 3 to 10,000 centipoise. Um, so regular flowing material, like regular paint.
Hmm. But it's application specific, yes.
Yeah.
Okay. She asked another question. How would we know if our particles are destroyed?
Yeah, well, that's a good question. You could look at under the microscope. Uh, so that's where you would maybe see that you're destroying your pigment particles.
Okay.
Um, Also, if you know you're not really, if you're just milling regularly, this is more with that comes into play with the fake pigments, like we see that with silvers and those metallic flakes. You would absolutely see it in the application process when you are, let's say, spraying out a panel and you no longer have good flake orientation, or instead of it being silver, it looks gray, or you're not getting the right color. That usually is indicative of having the an issue with your particles. So application parameters as well as electronic microscope to identify if something had gone wrong.
Okay. Another couple questions we'll breeze through here. Do all beads in the media mill have to be the same size, or can it be a variety of sizes?
No, they should all be the same size, because if they have different sizes, your kinetic energies are different. And what happens is the bigger beads will wear down your smaller beads much faster.
Mm.
And then you have very uneven processing parameters, and you can't really replicate that entire trial again if you don't know, uh, how your beads are wearing. You always want to use one standard bead size. Also, for smaller beads, you need a different screen size. And if you have varying media sizes, it's difficult to dial in the proper screen. Otherwise, you can clog the screen if your screen is too large for the larger particles. If you're smaller, sorry, larger beads. If you have smaller beads, then they could clog that larger screen, so that would not be advisable. Then you don't have any flow of your slurry through the milling chamber or basket.
Okay. Yeah, totally makes sense. Last one here from Tim. What are the pluses and minuses of a basket mill relative to a three-roll mill?
First of all, safety, right? Three roll mills are not very safe. I mean, they have done some design changes. Um, I would say maybe cleaning. It's very easy to clean a basket mill. I can maybe do a quick job in about 5 to 10 minutes, and maybe 30 minutes to properly clean it. I don't know different three roll mill designs, but they're just kind of a bit more of a challenge sometimes to really clean them properly. I think a basket mill is very easy to clean.
Okay.
I don't know about cooling, but I would say probably cooling. You have really good cooling with the basket mill because of the double wall, and we have also cooling our supply vessel, so that might be an aspect. Um, it would be good. I don't know. It depends on some materials, but we have a lot of people moving away from three roll mills, and they like to have good safe milling down to really small particle size. So if they can, they use a basket mill.
Nice. And like Andy mentioned too, we have a facility in Wallingford, and Andy, you're there today, right? Is that right?
I'm here today. Yes, that's correct.
Okay. Yeah. So for visiting, running any trials, doing any tests, we're available for that. If you have any questions that you think of after the fact, just hit reply to any of the automated marketing messages you get. Myself or one of my colleagues will get that, and we'll funnel it to Andy or the appropriate person. Um, so with that, I think we'll wrap it up here. Appreciate your time, Andy, and expertise as always. Thank you to the attendees. Hope you learned something today. And we look forward to seeing you on a future Bitgardener web seminar. Thank you and enjoy the rest of your day.
Thanks, everybody. Have a good one.